Welcome and hello to another episode of Inside XRF. My name is Konstantin Brenkens, and today's topic is platinum ware in XRF, and specifically, how do you treat your platinum in the correct way, in the proper way, so that it lasts for a very long time? And yeah, as usual, if there is any questions, feel free to write them in the chat. We'll get to answering the questions in the end if there is time. Otherwise, we'll come back to you via email and see that we get all the questions answered. All right, so let's get started. First of all, a clarification, basically, when we're talking, why is this not working? There we go. When we're talking about platinum or platinum ware, it's important to note that this is not real platinum. There is, in German, there is this word Geräteplatinum, which basically transfers or roughly translates into platinum ware. Basically, we're talking about all the platinum ware inside a laboratory. So we're talking pliers, we're talking vessels, and so on. And in general, these are all alloys. Pure platinum would usually be too soft, especially if you use the platinum ware in a process with high temperatures, because pure platinum would deform at around 700 to 1000 degrees centigrade. That means a crucible would not be stable. It would start to deform and bend. So what is usually done is that we alloy the platinum, or well, the manufacturers alloy the platinum with the other precious metal. And that gives it a sort of mechanical stability. It hardens the piece that you are using, while retaining all of the chemical resistance that platinum offers, which makes them so desirable as a vessel. There is a little list here of different alloys that are used commonly in laboratories. So there is iridium, there is some rhodium added. We in our laboratory here at FLUXANA are using these vessels mostly for fusion applications, doing these tetraborate beads. We are using the platinum gold alloy, which is 95% gold and 5% gold, 95% platinum. So as I'm sure you're all aware, we're using samples and tetraborate in our fusion devices to make these nice fuse beads that we then analyze with the X-ray. And the fusion process, of course, takes place in these machines. And well, the dishes we are using are mainly platinums. And we are talking, the alloy we are using here is the 95% platinum, 5% gold. There are a lot of other ones, as you have seen in the table before. Also, there are different alloys between platinum and gold. There will be an example later where there is also a 90-10. So if you wanna, if you're looking into other applications other than fusions, there is a lot of information available on the internet regarding those different alloys and what they are best used for. Our presentation today, our topic today, is mostly based on this 95.5% gold. But I think a lot of these experiences that we have from our lab can be transferred to other platinum ware as well. So coming back to our specific alloy, the gold content in these crucibles and molds is extremely important. The gold prevents our liquid fusion from sticking with the platinum. And this is especially important in the casting molds. The gold prevents the fusion from sticking to the surfaces of the dishes when it is cooling down and solidifying. So you have to make sure that the gold is like you want those 5%, and over the time we'll come to that a bit later. Over the time this changes, and then at some point you have to be doing a recycling circle for this. So one thing to keep in mind, the gold is critical here because it affects directly the function of our platinum ware when it comes to the fusion and the fusion machines. There is different sizes for the crucible. Main difference is here is that depending on what equipment you are using, they will have other a different shape of these pins to hold them into a machine. For example, the three here on the left you are seeing, these are the ones for our electrical machines, and this is the one for our gas machine. It's just a different way to put them into the equipment so that they rest. But there is also other differences like the shape and the size. We have basically small ones and large ones we use. Based on how much fusion mixture you use, you will pick one or the other. And there is also some special, like a special one which has some sort of dents in there to increase agitation. And yeah, depending on what you want to do, you will choose one form or the other. There is also the option to number them when you order, just to have a protocol later how often they are used. That's what we like to do so that we can keep like a record basically of how many fusions were done in a particular piece of platinum ware. And the casting molds are available in different diameters. A few examples are here. So that when you make a dish or a fuse bead, it will fit into the cassette of your X-ray later. So most machines are a bit flexible, but some machines only allow like 32 millimeters, while other ones have maybe 32 and 40 and so on. So depending on your X-ray cassette, you will choose a size there. Automatic fusion machines. Pretty sure you're familiar with those two. We have the electrical one on the left here and the gas one on the right. And one thing to keep in mind when you're running a gas fusion machine, and that's true again, this is a general rule, you want to make sure that your gas flame does not have a reducing effect. One of the problems with damage to platinum or wear and tear comes from the conditions it is heated up in. And if you have reducing conditions, for example, due to your burner not having enough oxygen, that can be a problem in certain samples. So, for example, our machine, the gas is formed with propane and pressed air, but also there is an oxygen line in there to prevent this from being reducing, like from prevent this, the flame from being reducing. So we want to make sure that is okay. There is a alternative setup to do ICP solutions. In that case, we only use the crucibles in platinum. The target here, that is a Teflon beaker with an acid. So we basically pour in the liquid fusion into the acid to then form or dissolve a liquid for ICP real quick. We use the same crucibles here. One special mention, there is this special alloy which is called FKS. That's again a German short, Feinkorn stabilisiert. Basically, the problem with the platinum is all of them are exposed to thermal and mechanical stress due to the way they are used in the fusion process. And that also means they have to be recycled at a certain point. All of them. There is no exception. You can't use them forever. And of course, you do want to keep them for a long time. And this is where the FKS comes in. There is actually some zirconium oxide added to the alloy, and it affects the structure of the platinum ware or of the alloy, and it makes it more resistant. It actually has a longer service life. So the standard one will have 100 fusion, and the FKS will maybe have 200 or 300 fusion. So they are a bit more expensive, but in the long run, they can save you money because you don't have to recycle them that often. Now, on to handling. A few general rules. You only want to use you only want to touch hot platinum with a plier that has these little platinum shoes. Having hot platinum touch cold metal is generally a bad idea, so avoid it. there is this rule that you want to make sure that your workplace is clean. Beware of dusts; they can cause problems. Wearing gloves is recommended, and especially with the casting molds, you want to be extremely careful when handling because of the polishing in the middle. They are finished with a special polishing, and each scratch here, which can be caused by uncareful handling and can cause problems later, and they might lead to an early recyclement being necessary because they just don't work anymore. In our lab, we like to use these little trays here. You can see we simply avoid touching our platinum when it's unnecessary. So for transport, we like to put them in these little trays, and they are actually available now at FLUXANA if you're interested. It's just a good way to just carry them around from one workstation to another. For the dishes, we like to have this one. I think there in the next picture is when it comes to cleaning, the first question is, when do we clean each piece? Basically, we clean in the ultrasonic bath. There is more details in the next sheet. We do that for the crucible after each fusion cycle. So each fusion, afterwards we clean, then we do the next fusion. For the casting molds, that is usually not necessary. We usually leave them on the machine for, let's say, a work day, and we only clean them if there was an accident or if it's let's say, a special aggressive sample. And again, we want to be very careful handling the platinum molds. So for cleaning, we always use this little holder. We put them in like sort of in a washing machine, and we never put them together with the crucibles. They always get their extra separate beaker so that we avoid scratching and whatnot from the parts touching and being exposed to the ultrasonic waves. Yeah, the setup in our laboratory is similar to the picture here. We have a beaker, 600 milliliters. That's where the acid goes in, and that's where your platinum goes in. This one is then put into a ultrasonic bath, and the basin is filled with just plain water, and we always add a little drop of soap or detergent. Just helps with the ultrasonics. It reduces the tension, so it helps the effect. And these baths can be heated. It's not necessarily needed, but some people prefer to it because it goes faster. One thing you want to be very careful about in this setup is there will be splashes from the acid in handling. So, for example, this metal cover here should be replaced with something non-corrosive. We'll see in the next picture we actually have a Teflon cover. And you also want to be very careful not to get the acid splashes inside the water. That might damage your platinum basin over time, and then you have to replace it after a year or two, which is not nice. And you also want to make sure that there is no contact from the beaker with the metal part of the basin. This might cause friction, and then they rub together, and then again, the basins, say like the ultrasonic basin, it just suffers. And it suffers from the fumes enough, so you want to keep it as safe as possible. So what acid do we use? There is multiple options here. Citric acid is one that people prefer because it's easily available and not very hazardous. You can heat it to 50 or 80 degrees. What does FLUXANA use? We are actually using HCl here because, well, it works for us. It goes very fast. And yeah, the idea is you leave it in the basin, you give it the ultrasonic treatment for a few minutes, and then you take it out like my colleague is doing here. You wash away the acid, and then you clean it with the ionized water, and then it goes into a drying cabinet. So yeah, FLUXANA is doing, like I said, we are using HTL 18%. We can just buy that in a big canister. We use a beaker roughly a week. At the end of the week, usually it gets replaced. We wash off the acid residue, then we rinse with the ionized water, and then it goes into the drying cabinet. Of course, observe PPE here, like my colleague is doing. You know, you want to wear the gloves, you want to have like safety goggles, or like she's doing here, like a full sheet, because acids you don't want to get into your face. I think that's clear. There is an old habit that people use platinum ware and for cleaning they heat it up. They don't put anything in there, but they put it in the furnace so that every contamination or every dirt gets burned away. That is a very bad idea. So the problem with cleaning platinum by just heating it up to a high temperature is that it can cause this so-called platinum corrosion. We'll get into the details there. So we definitely recommend not to do that. In case if you want to do an extra thorough cleaning or an extra very high intensity cleaning, let's say, what we always do is what we call a cleaning fusion. That means we take our tetraborate, our flux, usually the one that we use for samples as well, and we add a bit of additive into there so that it flows more easily. And then we just do a blank fusion. So we make a cleaning program on one of our machines, for example, and we only put flux and a bit of additive. And then we make a quick run and throw away the bead. But that helps a lot with just cleaning out the platinum wear after difficult samples, let's say. There is this known effect from some analytes, copper and cobalt being the most known here. They creep into the platinum wear. There is this what they call memory effect. What that means is if you do one sample and it has copper and cobalt and you do not make a special cleaning afterwards, you will find 500, 300 ppm of that copper or cobalt in your next sample, even though that sample didn't contain any. Because what happens is that these elements go into the dish and then the next sample that doesn't contain them, they get washed out again. So there is a problem with cross-contamination, and you want to be very careful if you find materials or samples that have this nice blue color. The nice blue color is always an indicator there is some copper or cobalt involved here, and it makes sense in that case to either do extra cleaning afterwards or do a separate set of platinum that you only use for these samples. So to have a special set of platinum just for copper samples. Both strategies are viable. So coming back to the platinum corrosion that was just mentioned. We have some nice pictures here of what it looks like in reality, especially like this one down here. You don't want that to happen in your laboratory work. So the question always is, where does this come from? And there is this German verse that I will not bother reading it to you, but the translation is basically, there are some elements that are a high danger to platinum in general, and these elements are listed here. And you don't want to put them into your crucibles made of platinum and then heat it up, because this can lead to this platinum corrosion. And one thing we need to understand, I don't want to go into too much details here. There is plenty of information available on these effects on the internet if you're interested. But basically, what we need to understand, platinum corrosion is not something like a conventional corrosion where we have acids, or in case of iron, where we simply have rust destroying something chemically. What happens in platinum corrosion, or the way it's understood, is basically that the platinum forms an alloy with the element that is present. And this alloy then, again, forms another alloy with platinum, and during this process, the melting point gets rapidly reduced. So in case of our example here, we have a platinum arsenic system here, and I'm actually in the way here. I just need to move that. You see, so pure platinum would have a melting point round about 1,700 degrees. And now if we mix this with arsenic, the melting point drops down to like 1,400. Like, this is a steep drop already. But now the problem is, if that one alloys with platinum, the actual melting point, it's down here. It's only, it's only 600 degrees. So we have kind of cascading effects, and our fusion actually happens at that way, at that temperature range. So the problem with certain elements is that they can form alloys with the platinum, and they drastically reduce the melting point of our alloy, making it possible to actually well, disintegrate. And these elements that were mentioned before here that can have this effects, they're usually called platinum poisons. And so we'll have a table in one of the next sheets to show and yeah, what elements are dangerous to platinum. If you want to have a look at the description, this whole thing is called eutectic system. Eutecticum in German. Wikipedia has a nice entry on that if you're interested in the real effects. But yeah, basically we want to understand platinum corrosion usually means that there is an alloy forming and that can potentially damage our platinum vessel, our dish, or our casting mold. So let's have a look how that works in our field of work. So when we have anything metallic in our sample, be it a ferroalloy or be it a contamination, this can cause this effect. So a general rule of doing samples is make sure they are not metallic, because depending on the alloy, the fusion temperature that we are operating our equipment at, which is around 1200 degrees, that is enough for platinum to form alloys with a lot of elements. And effectively, this is what happens here. Somebody did not pay attention here. They had like large particles in their sample, and what effectively happens is you have this alloy forming, this effect happening, and it just eats a hole in your platinum crucible. So be careful of metallic components. Generally speaking, oxides are harmless. Even the oxides of the mentioned platinum poisons, as long as your sample is oxygen bound, is an oxidic form, that usually means it's no problem. So arsenic will be a problem. Arsenic oxide is not a problem. So one thing to keep in mind. Let's have a look at a few known poisons and what happens here. So yeah, anything metallic, ferroalloys or metallic particles as a impurity, they are dangerous because they can form the alloys. And you can find these in, of course, ferroalloy samples, but also in recycling materials. There is one specific problem we are now having with aluminum oxide, actually, which comes from recycled materials. Sulfides do lead to something like brittleness in the platinum. You find that in, for example, a lead sulfide concentrate, which are common ores. So you want to be aware of that. Carbon is another problem because carbon can reduce other elements. For example, carbon in a casting powder can lead to other elements in the sample being reduced back to the metallic state. And then we are back up here. We have a poison that forms an alloy. Phosphorus is known to have this effect of, again, making the surface very brittle and leading to a lot of wear and tear and the need to be recycled very often. This happens in foodstuff, and one way around it is to use a different platinum gold alloy. They actually recommend that if you're using phosphorus samples in the food industry, use platinum gold 9010, because that seems more resistant to this effect in comparison to our 95.5%. Sulfur in general also same effect as the phosphorus. Basically, it kind of has effects on the surface and it increases the aging. We find this a lot in slag samples. So be careful with sulfur and sulfide samples. SO3 sulfates are not a problem usually. So yeah, you want to be oxidizing before. Last but not least, carbides combine all this effect. So if we're looking at silicon carbide, for example, you have the effect of the carbon here being a reducing element, and at the same time we have metallic silica that can directly damage your platinum. So you basically have the worst of all. Be very careful with carbide samples. They can be done. You have to just stick to a few rules. So how can they be done in fusion? Well, same as we have mentioned in some of our other webinars about metallic samples or metal alloys, you do the oxidization before. So you can see here our adjusted principle of fusion. We mix a sample with an oxidizer, we oxidize before, and then this oxidized sample gets mixed with the tetraborate to do the fusion. There is multiple approaches here. Don't want to go into detail. This has all been discussed somewhere else. Generally speaking, you can make it in 2-step or you can make it in 1-step. Depending on your equipment and sample, there is different advantages to both approaches. But generally speaking, we oxidize the sample before we do the actual fusion. That's the idea. Speaking about oxidizers, we have a table here, but we're kind of running short on time actually, so I'm skipping this one. It has been mentioned in some of our other webinars as well, so feel free to check our website for more details about this. One new thing I want to briefly touch on is this wet chemical oxidation with HNO3, with nitric acid. This is very effective for these aluminum particles because what we found and what a lot of people have seen in the recent past is that a lot of recycling materials, secondary resources basically, they come with these passivated aluminum inside. So the problem here being is you have an particle that has a metallic core of alumina and then an outside shell of alumina oxide. So from the outside, you can't get to the metallic core. Well, at least not thermically by just putting it in a furnace. Now, when this is going into fusion, when you dissolve it in tetraborate, it actually becomes like a very reactive thing, and it has this effect on platinum that it has a very high wear radius on your crucibles. They don't destroy a crucible immediately, but you can see something like this or something like this after just doing one fusion with these materials. So you want to be very careful with that. And one solution is to make this dissolving in acid and then just drying it again. But also, if you're unsure about your sample, you can use a test crucible, like for example quartz, to check if your sample have this effect before you actually use your standard laboratory platinum ware and well, yeah, you endanger it, so to say. The effect of carbon, again, just a few examples. I mentioned before the carbon kind of has an increased wear, and you can see this here. This is a new crucible, and this is one that has been done like a few hundred samples. And with samples that contain a lot of carbon, you can see this happen very quickly. It's not necessarily a problem, but you want to make sure that you recycle your platinum ware more often then. How do we find out if our sample have a carbon? Well, you can actually see if you're doing a fusion and it comes out like this, that means there is a lot of carbon in your sample and it has this, yeah, this haze basically. So what you need to do here is get rid of that before you actually do fusion. And it's pretty simple by just doing what we call a pyrolysis. So you basically, you don't mix the sample in your flux, you put it on top, and then you do a low temperature step to burn away the carbon, and then you rank up to a fusion temperature. And that usually works fine with samples containing carbon and also samples that contain a lot of organic materials. We need to get rid of that before we actually do the fusion. Oh, that was the wrong button. General handling advice, just to kind of sum it up. The samples or the platinum gets dropped. It's just that happens in laboratories. So having a dent in your crucible is generally not a problem, although you want to be careful. Remember the little tray I showed in one of the earlier samples? It's a good idea for handling because it just avoids you and your staff dropping stuff. So dents usually don't matter really. It increases the cleaning time in the ultrasotics, but otherwise it doesn't really matter. There is this effect that these little pins that hold the crucible in position, they deform over time due to the thermic and mechanical stress. So what happens is with time, they look like this. They usually bend downwards. So what you want to do is straighten them out every now and then. If you see a crucible and you see it's a bit bended, just take some pliers, bend it carefully back into a straight position, and you're fine. Usually the ring can handle the stress. You don't want to put them like this in your machine because there is the danger that they simply drop out of, and then you have a big mess in your fusion equipment. So you definitely want to avoid that. Casting molds, yeah, very careful with those. As I mentioned before, the gold contents changes, so we have to recycle them at one point. We cannot repolish them because repolishing would make the surface nice again, but it would not get the gold back in. So recycling is a must here. You want to be careful with cracks and a surface like, for example, this is okay. You can see this one is way past its service date. This one needs to be recycled. And we definitely not recommend to repolish it because that causes more problems than you solve. We have to keep in mind that the dish is part of our analytic system. Like a new dish looks like this, is very flat. So the distance to your X-ray tube in measurement is very constant. Now over time, they will bend like this. You can see the dent here in the middle, and they will bend down like here. But what happens is now you change the distance to your X-ray tube, and that can have effects on your analysis. Usually what you find is that your sample your sum of analytes is more than 100%, and you can usually see an increase in the main components. So that's a clear sign that your dishes need to be replaced, and you can actually use this effect using a control sample that you do regularly, and then you can see when it's time to replace your casting molds. Crucibles can be used for a longer time, but at some times, if there is an accident and you feel that it has been damaged, recycle it immediately. It's not worth the risk of your equipment, of your fusion equipment, using half-damaged crucibles. And in this case, if this one will take a lot longer time in cleaning because of the rough surface, and at some point it just becomes a nuisance. So if cleaning takes longer, like 10 minutes, that's a good sign to recycle them as well. Last remark here, like we've been talking about platinum a lot now. There is different materials for fusion also that we can use with, different materials for the crucibles that we can use in fusion. So example, there is this metal zirconium, that's this one in the picture, which is used for peroxide fusions, for example. And there is also quartz, which is this one, which is perfectly fine for catalyzers where we're actually looking for platinum. So using a platinum vessel is a bad idea. So there is alternatives if platinum is not feasible. There are some other ones. And yeah, usually they fit in the same machine. Sometimes they need some sort of adapter. As you can see here, these are the zirconium ones in an adapter ring, and it goes on the same fusion machine. And yeah, let's come to the summary. So how long or how can you extend the life of your platinum? You definitely want to be careful with your handling. Gloves and handling and holders is a good idea. You want to avoid any mechanical cleaning and any mechanical damage. So just don't rub the sample, especially not the dishes. Don't rub them with your lab coat. Not a good idea. Cleaning in acid bath is a good idea. You can do the cleaning fusion for special samples. Having extra crucibles for problematic samples, the ones with the memory effect, is a good idea. You want to keep your melting temperature at a reasonable level. Don't overheat it because that will just increase problems with alloying and so on. And last but not least, you want to have clear oxidizing conditions all the time, inside and outside of your dish, because this can be the major problem. There is a very known history about people using silicon carbide as their surfaces for working. And also, for example, in furnaces, they used silicon carbide resistors, basically. And if they got in contact with platinum and you later heat that platinum, there was a very high chance for them to destroy the surface. And in worst cases, they actually just ate a hole straight through the platinum. So you want to be very careful with handling then. And in terms of sample, oxidization is the key here. Get everything into an oxidic form, and then the danger of your platinum being damaged is very low. All right, only 5 minutes over time. I call that good. I'm afraid we do not have time for answer any questions here. I see there are a few, but we will get back to you by email. Thank you very much for your attention and have a nice day. See you next time. Bye-bye.